Hello everyone, welcome to MachineX webinar. Today's my topic is state of art image processing across different domains. My name is Shubham Goyal and I'm a data wizard at MachineX. So let's move to the our today's agenda. So today we are going to talk about image processing history and different approaches to achieve image processing. Then we will talk about a little bit about residual neural networks and the performances of residual neural network and different approaches. Then I have a little demo application for you all using these image processing approaches. Now, before we jump into the main topic, I would like to talk a bit about our tribe MachineX. So, MachineX is a group of data wizards who love to play with data and create wonders out of it. And along with that, it's a service provider who gives solutions to different clients on AI and ML. It is a group of thinkers who loves to contribute to the development of AI and ML, and hence you can see the things we are doing. We built a library called KSAI, which is an ML library consists of various algorithms written in Scala. We regularly post blogs on various ML and AI topics. We do internal knowledge sessions as company culture and release them on YouTube so that others can also view and learn from it. Apart from sharing our knowledge about ML and AI, we are going to release one of our product called Maged. Maged is an intelligent meeting assistant tool which can do a lot of wonders while attending meetings. It will give video recording facility, and along with that, it will give the AI powered features like automatic action item generation, emotional analysis, facial detection, and many more. As you have already imagined, if you have these powers while doing meeting, you can compete with Sherlock Holmes. Jokes apart. So this is how our Maggot dashboard is currently look like. Surely we are going to add some more features in it in coming time. Apart from Maggot, we have a different product we are working on, and that is Fisheye. Fisheye is an intelligent marketing tool which helps you to identify potential target companies. Like in this screenshot, I had opted for a company in sector artificial intelligence, which is located in like its location should be in United States, and the company size should be 0 to 500. As I already told you, we had built a library called KSAI, and it's a machine learning library written in Scala. It also you can also contribute to this library. Just go on GitHub and search for KSAI. Every open source idea from you is heartily invited. Moreover, we regularly do our innovation projects in our innovation labs. We do TOK sessions, and as I already told you, we publish them on YouTube. We regularly contribute to society through blogs and open source contributions. And last but not least, we have many certified professionals in machine learning and deep learning. So this is all about MachineX. Uh, Now let's move to our main agenda, that is state-of-the-art image processing across domains. Before that, let's talk a little bit about image processing. So image processing is a method to perform some operation on an image in order to get an enhanced image or to extract some useful information from it. It is basically type of signal processing in which input is an image and output may be image or characteristic or features associated with that image. Nowadays, image processing is among rapidly growing technologies. It forms core research area within engineering and computer science discipline too. So there is a vast difference between image processing, how it was done in past years, and how it is like all AI engineers and machine learning engineers doing it in these days. So let's talk about the traditional way of doing image processing. So the traditional pipeline for image, okay, we are talking about image classification here. Uh, the traditional pipeline for image classification involves two modules. The first one is feature extraction, and the second is classification. It is also same for today's process, but the way they are achieving these modules, they have a different problem. Okay, like feature extraction previously in like it's involved extracting a high level of information from raw pixels value that can capture the distinct among the categories involved. The feature extraction is done in a unsupervised manner, wherein the classes of the image have nothing to do with information extracted from pixels. So some of the traditional and widely used features are GIST, HOG, SIFT, and LBP, etc. So after the feature is extracted, a classification module is trained with the images and their associated labels. A few examples of traditional module are SVM, logistic regression, or we can say random forest and decision tree, and so on. So what was the problem with these methods? The problem with this pipeline is this involved too many heuristic as well as manual labor to tweak parameters according to the domain to reach a decent level of accuracy. By decent here, I mean reaching close to human level accuracy. And that's why it took years to build a good computer vision system like OCR, face verification, image classifier, and many object detectors, and so on, that can work with wide variety of data encountered during practical application using traditional computer vision. And the another problem with this method is that it is completely different from how we human learns to recognize things. As you all know, AI and its all subdomains are inspired by us, the humans. For example, just after birth, a child is incapable of perceiving his surroundings. But as he progresses and processes data, he learns to identify things. This is the psychology behind deep learning, wherein no hard-coded feature extractor is built in. It combines the extraction and classification modules in one integrated system, and it learns to extract by discriminating representations from the images and classify them based on supervised data. So, image processing, or we can say image classification across all domains. If we have to see some applications of image processing in nowadays, the first come strike my mind is healthcare section or healthcare sector. So imagine being able to detect blindness before it happen. Million of people suffer from diabetic retinopathy, retinopathy, and the leading cause of blindness among working aged adults is diabetic retinopathy. Many hospitals in India hope to detect and prevent these diseases among people living in rural areas where medical screening is difficult to conduct. Solution using artificial intelligence or image processing will improve the hospital's ability to identify potential patients. So, okay, guys, I am seeing a lot of people are asking questions. So you can write down your questions here, and I will follow up you with like follow up you after this session. So the another application is pulmonary chest X-ray defect detection. So imagine we can accurately detect whatever problem is there in X-ray, and that too with increased accuracy. and accurately. So the another sector is manufacturing sector. As we all know, steel is the one of the most important building materials of modern times. Steel buildings are resistant to natural and man-made wear, which had made the material ubiquitous according to or around the world. To help make production steel more efficient, image processing can help identifying defects, or image processing or computer vision system, or we can say intelligence system, can monitor products for their quality control. So whenever I think about image processing or computer vision problem, there is one algorithm strike my mind, and that is convolution neural network, or we can say CNN or ConNet. So a convolution neural network are a special kind of multi-layer neural network designed to recognize visual patterns directly from pixel images with minimal pre-processing. Several pre-trained models used in transfer learning, and they are based on large convolutional neural network. In general, CNN was shown to excel in a wide range of computer vision tasks. Its high performance and its easiness in training are two main factors driving the popularity of CNN over the last few years. So a typical CNN has two parts. The first one is convolution base and the second is a classifier. So a convolution base is composed by a stack of convolution and pooling layers. The main goal of convolution base is to generate features from the image. For an intuitive explanation of convolutional and pooling layers, you can refer to the Nolder's blocks. You can just write about convolution neural network on Nolder's block, and you get a number of blocks there. The second part is the classifier, which is usually composed by fully connected layers. The main goal of the classifier is to classify the image based on the detected features. A fully connected layer is a layer whose neurons have full connections to all activation in the previous layer. So as I already told you, there are different pre-trained models which use transfer learning for these image processing tasks. So let's talk about a little bit on transfer learning. So a transfer learning is a popular method in computer vision because it allows to build accurate models in a time-saving way. With transfer learning, instead of starting the process or the learning process from scratch, you can start from patterns that have been learned when solving a different problem in a different situation. In this way, you can leverage previous learnings and avoid starting from scratch. So, the transfer learning is an application of skills, knowledge, or attitudes that were learned in a one situation and we can apply it in another situation. Transfer learning is usually expressed through the use of pre-trained model, as earlier told you. So suppose a teacher has a year of experience in a particular topic he or she teach. With all this accumulated information, the lectures that students get is a concise and brief overview of that topic. So it can be seen as a transfer of information from a learned to a novice. Keeping in mind this analogy, we compare this to neural network. A neural network is trained on the data, and this network gains information or knowledge from this data, which is combined as weights of that network. These weights can be extracted and then transferred to like any other neural network. So instead of training the other neural network from scratch, we transfer the learn feature. Let me take an example, simple example, so that we can know the importance of transfer learning. So let me take an example of tribal growth, tribal knowledge growth. Before our language was invented, what was happening is the amount of knowledge passed down from one generation to the next generation was very low, and the amount learned by the particular generation was also uh, not large, or we can say very small. So what was happening is there was no medium to transfer the knowledge from one generation to the another generation, and on other hand, within the generation, people have to start learning things from the scratch, or they have to invent things and then learn those things and apply them for their use. So these were the two problems we just discussed, like less learning rate in each generation, number of knowledge amount was less. But after our language was introduced, the numbers and the stats are totally different. The amount of knowledge passed on from one generation to the next generation was like quite high, and the amount learned by a particular generation was also high, because they have the learning from previous generation and they have their own learning too. So this is how our transfer learning can like improve accuracy and the knowledge of a particular thing. Transfer learning is not only improving computer vision and image processing tasks, but it is also changing our way of doing machine learning. So a traditional machine learning was isolated and single task learning. Knowledge is not retained or accumulated. Learning is performed without considering the past learned knowledge in other tasks. Like on the left side, we have on the left diagram, we have the dataset one, and we do in task one, like we are making our learning system with particular dataset one. When we encountered with dataset two, we have a different learning task, task two, and we are not considering the knowledge gained by dataset one. On the other hand, the right hand side, what transfer learning is doing, so transfer learning like relies, or we can say we can make it relies on the previous learned task. So learning process can be faster, more accurate, and it will need less training data. So on this diagram on the right hand, we can see that we are training our task one or task one learning system on dataset one. We are storing every knowledge of task one and using it for the another situation, or the another time we are encountered with dataset 2, so that it has now the learning of task 1 and the learning it gained from the dataset 2, so that it can make these like results or decisions more accurately. So, uh, in this webinar, we are talking about current state of art in image processing or image classification. So, there are different convolutional neural network architecture introduced nowadays for these, like for achieving transfer learning. So, these CNN architectures are actually pre-trained models which are using through transfer learning for our different tasks. So let's understand various architecture of convolutional neural network. These are ResNet, AlexNet, VGGNet, and Inception. So from where these architectures are introduced is there is a contest named ImageNet Large Scale Visual Recognition Challenge. So this ImageNet is a large dataset of annotated photographs intended for computer vision research. So the goal of developing this dataset was to provide a resource to promote the research and development of improved methods for computer vision. Based on statistics about the dataset recorded on ImageNet homepage, there are a little more than 14 million images in the dataset, a little more than 21,000 groups, or we usually say classes, and a little more than 1 million images that have bounding box annotation. For example, boxes around identified objects in the image. So let's talk about our first CNN architecture. that is AlexNet. So AlexNet was born out of need to improve the result of ImageNet challenge. Like previously we had like LayNet and different models, but they are not up to the mark, or we can say they didn't have that much accuracy on ImageNet dataset. So AlexNet was one of the first deep convolution neural network to achieve considerable accuracy on 2012 ImageNet challenge. And AlexNet has an accuracy of 84.7% as compared to the second best with an accuracy of 73.8%. So in difference of like around 11%. The idea of spatial correlation is an image frame was explored using convolution layers and respective fields. So AlexNet network consists of five convolution layers as you can see in this diagram. There are five convolution layer followed by max pooling layer and three fully connected layer after these convolution layer. So the activation system or activation function used in AlexNet is value function. The structural detail of each layers you can see in this diagram. So the network has total of 62 million trainable variables. The output to this network is a batch of RGB images of size 227 into 227 into 3 and an output of 1000 into 1, and it is an probability vector and it correspond to each class. So AlexNet used data augmentation to reduce overfitting. This data augmentation, including mirroring and cropping the images, to increase the variation in the training dataset. The network uses overlap max pooling layer after the first, second, and fifth convolution layer. Overlapped max pool layers are simply max pool layers with strides less than the window size. 3 into 3 max pool layer is used with a stride of 2, hence creating overlapped receptive fields. This overlapping improved the top 1 and top 5 error by 0.4% and 0.3% respectively. So before AlexNet was introduced, the most common used activation functions were sigmoid and tan. Due to saturated nature of these functions, they suffer from the vanishing gradient problem, and it makes difficult for the network to train. AlexNet uses ReLU activation function, which doesn't suffer from the vanishing gradient problem. The original paper shows that the network with ReLU achieved 25% error rate, about 6 times faster than that the same with 10 or sigmoid nonlinearity. Sorry guys. Although ReLU helps the vanishing gradient problem, but because of its unbounded nature, the learned variable can become unnecessarily high. In order to prevent this situation, AlexNet introduced local response normalization, or we can say LRN. The idea behind LRN is to carry out a normalization in a neighborhood of pixel, amplifying the excited neurons while damping the surrounding neurons at the same time. So there was some problem with the AlexNet as it's using too much number of parameters. So it make it a little bit there was a problem while training the AlexNet. So VGGNet was born out to need to reduce the number of parameters in a convolution layer and improve on training time. There are multiple variants of VGG, like VGG 16 with 16 layer and VGG 19 with 19 layers, which differs only in total number of layers in the network. VGG 16 has a total of 138 million parameters. The important point to note here is that all the convolution layer are of size 3 into 3 and max pool kernels are of size 2 into 2 with stride of 2. So this is the structural detail of VGG16. As I already told you, it has 138 million of parameters. So VGG, like it was very painful to train VGG because uh, like it reduced the number of parameters, but it was very painful, slow to train. And the feature which VGG net comes up with, spatial pooling, is like carried out by 5 max pooling layers, which follow some of the convolution layer. So, as of now, it is witnessed that we had architecture or CNN architecture mostly between 16 to 30 layer, or we can say the maximum of 30 layers. Uh, Despite the popular meme shared in AI communities from the movie Inception, uh, I hope you all had seen the movie Inception, and this guy is favorite, my favorite. So the movie is stating that we need to go deeper. So empirically show this statement shows that there is a maximum threshold for depth with the traditional CNN model. As an answer or as a result, there is a thing introduced called deep residual learning, or we can say ResNet. So, uh, like our hierarchical feature and role of depth, or we can say depth of these layers, its role is to identify low, mid, and high level features. It was assumed that more layers enrich the level of the features, and the previous ImageNet models, as I already told you, are of depth 16 to 30 layers. So the main question here is learning better network as easy as stacking more layers. So in short, can we have a better learning network by stacking more and more layers over each other? So ResNet research paper opens with this answer to this. They trained a plain convolutional neural network of 20 layer and 56 layer, and we can see the result in this diagram or this figure. So this plot defies our belief that adding more layers would create a more complex function. Thus, the failure would be attributed to overfitting. If this was the cause, additionally, regularization parameters and algorithms such as dropout or L2 norms would be a successful approach for fixing these networks. However, this plot shows that the training error of the 56 layer network is higher than 20 layer networks, highlighting a different phenomena explaining its failure. As I already told you, these evidence shows that the ImageNet model using convolutional and fully connected layer typically contain 16 to 30 layers. ResNet also comes up with constructional insight of an like good or ideal convolutional neural network architecture. So it should consider a shallow architecture and its deeper counterpart. So a deeper model would just need to copy the shallower model with identity mapping, and the constructional solution suggests that a deeper model should produce no higher training error than its shallower part or counterpart. So the failure of 56 layer CNN, as I already told you, blamed on optimization function, initialization of the network, or the famous vanishing gradient problem. Vanishing gradients are especially easy to blame for this. However, the authors argue that the use of batch normalization ensured the gradient have healthy norms. Amongst the many theories explain why deeper network fails to perform better than their shallower counterparts, it is something better to look for empirical results for explanation and work backward from there. The problem of training very deep network has been alleviated with the introduction of new neural network architecture, that is the residual block. So the picture here is the most important thing to learn for developer. It is looking to quickly implement this and test it out. The most important modification to understand is the skip connection or identity mapping. This identity mapping does not have parameter and is just there to add the output from previous layer to the layer ahead. However, sometimes x and fx will not have the same dimension. Recall that a convolution operation typically shrinks the spatial resolution of an image. For example, if we have 3 into 3 convolution on a 32 into 32 image, that result in a 30 into 30 image. The identity mapping is multiplied by a linear projection W to expand the channels of shortcut to match the residual. This allows for the input x and fx to be combined as input to the next layer. If we have to see the difference between a previous model VGG19 and a plane layer of 34 34 layer plane network and then 34 layer residual layer network. So the main thing to notice here is these dot lines in residual network. These are our skip connections which are taking input from our uh, like from our shallower part and give it to the next layer. So residual research paper comes up with this example by showing that it's the including of residual function uh, can be an answer for that vanishing gradient and overfitting problem. They train their architecture on 34 and 18 layers of ResNet architecture, and the straight line despises here the training error and the static line despises the testing error. The 34 layer ResNet achieves sub 30% error rate, unlike the plane network on the left plot. So the 34 layer ResNet outperforms the 18 layer ResNet by 2.8%. The skip connections between layers add the output from previous layers to the output of the stack layer. This result in the ability to train much deeper network than what was previously possible. The author of ResNet architecture tests their network with 100 and 1000 layers on a CIFAR10 dataset. They test on the ImageNet dataset with 152 layer, which still has less parameters than VGG network. An ensemble of deep learning, or we can say deep residual network, achieve a 3.57 error rate on ImageNet, which achieved first place in ImageNet contest classification uh, in 2015, or in late 2014. So if we have to summarize and like see the stats which are showing by these convolutional architecture, AlexNet was more deeper, or we can say first deeper CNN architecture. So AlexNet and ResNet 152 both have about 60 million parameters, but there is a difference of about 10% in their top 5 accuracy. VGGNet not only has a higher number of parameters and a flop as compared to ResNet 152, but it also has a decreased accuracy. Training an AlexNet takes about the same time as training the Inception, 10 times less memory requirement for training an AlexNet. So, in conclusion, the skip connection is a very interesting or interesting extension to deep convolution networks that have empirically shown to increase performance in ImageNet classification. These layers can be used in other tasks requiring deep networks as well as localization, semantic segmentation, or generative adversarial networks, or we can say GANs. Residual networks are different from LSTMs, which gate previous information or gain information such as that not all information pass through. Additionally, the skip connection shown in previous slides arranged in two-layer blocks. They do not use the input from the same layer 3 to the 8. Residual networks are more similar to attention mechanism, In that they model the internal state of the network opposed to the inputs. So this was all about our CNN architectures, and as I already told you, I have like uh, s- an application using these like CNN architectures, and that is malaria cell detection. So this is an web application to detect whether a cell image contain malaria infection or not. So let's go to the notebook of the same. So this is an Colab notebook, or I can say I am using Google Colab for its GPU feature. So here I am using the dataset from Kaggle, a home for data science. So I am just importing my Kaggle credentials by this command, and downloading the whole dataset here. Using the tree package, when I see my dataset, it is nearly about 13,780 entries for both, or we can say 13,780 images for both infected and uninfected cell images. So here I can see my CSV file. Uh, these are my images or the address of images, and these are the labels like the cell contain malaria or the cell is healthy. Here I am creating my train validation and test data set. Uh, Actually, we don't have the much time, so let me move forward to the main agenda. So here I am resizing my images. So I am making my images in a particular size or with the same size so that the training will be more accurate and more fast. If we have to see the sample cell images, this is how they look like. So these are the infection, or we can say malaria infection, consistent or consist in our blood cell images, and these are the healthy cells. So here I am setting up some configuration and scaling my images and like encoding those label classes. So I'm using a batch size of 62, 64, and we have two classes, like one is healthy and one is infected. I'm training my network up to 25 epochs. So the main thing start from here. Also, I'm using TensorFlow 2.0. So main thing is to see the architecture I'm using. So here I'm creating my simple CNN architecture from scratch. So I'm using three convolution layers followed by max pooling layers, and I have like uh, two hidden layers or dropout layers and one output layer using sigmoid function for image classification task. So this is how my structure of like plain CNN architecture looks like. It has this much of layers for our classification task. So when I train my model or I can say my simple CNN model up to 25 epochs, so it gains a training accuracy of uh, 99 99% and a validation accuracy of 95%. But the main problem arise when I see the training history. So as we can see in this diagram, our training accuracy after nearly fifth epoch getting even more vast, or I can say the validation accuracy is going vast with increasing of epochs. Also, our validation lost, or we can say validation loss value, keep on increasing after the fifth epoch. So I can save my model with simple command model.save, and after that our main things come like transfer learning. So I am using VGG19 network here, and it's very easy with TensorFlow to use these pre-trained models or pre-trained CNN architectures. I had earlier make an object of TensorFlow TF, so I have to write tf.kras.application dot whatever network you want to use. Either it's VGG19 here, or you can use ResNet 50, VGG16, or AlexNet. So here I'm importing VGG19 with all weights it learns from ImageNet contest or ImageNet dataset. I am freezing my convolution base so that I can leverage those knowledge or the feature extracted by ImageNet dataset. So here I am using the base VGG, means the convolution base will be of VGG, and I am adding my classifying layers into it. So when I see the summary of model or the structure of this model, I can see these are the like convolution based layer starting from block. So these are the freeze layers which will not train again. And these are the layers like dance 3, flatten 1, dropout 2, dance 4, dance or dropout 3. These are the layer I had added for the classified task. So we have in total 28 layers, and the total trainable layers are 6 because I had freezed all the convolution based layers. When I trained my VGG19 architecture, it gains somewhere 96% of training accuracy and a validation accuracy of 94%, which is low from my plain CNN architecture, which I had made from scratch. So, if we have to debug, we can see that our validation accuracy is fluctuating with every number of epochs, and it is not going that much high again from nearly 10 epoch. And this is like simply an overfitting. So we have to like add something or make our pre-processing of data even more accurate. So as I already told you, these pre-trained models used image augmentation for their accuracy or to like increase the number of data set so that it have number of or type of images while the training process. So here I am doing my image augmentation. It is also very simple with use of TensorFlow. We have to just import tf.keras.preprocessing.image.image data generator, and I am rescaling my image, zooming, like increasing my zoom range, and rotating images, and sharing images, and changing width and height of those images. So after data augmentation, this is how my images look like. You can see here I am flipping my image and rotate it by some degrees. Uh, After that, to like avoid previous training process, we have seen that there was a problem of overfitting with our VGG19 architecture. So now we will fine tune our pre-trained CNN with image like augmentation. So again, I had like imported VGG19 architecture and freeze the convolution base and added my like classifier layers. So when I train my fine-tuned model with image augmentation, after 25th epoch, it gives me 97% of training accuracy and then like best accuracy of like validation accuracy of 96%. So this is how image augmentation can make an impact on our learning process. You can also see many blogs on image augmentation on our like Nolda's Machine X blogs website. So if we see the training process now, so the training process is like good for after we added image augmentation in our learning process. So now we just have to save our model with model.save. And if I have to evaluate my like all of the three models, so my basic CNN got an accuracy of 94.97 percentage. My VGG19 frozen got 93.76% of accuracy, and my VGG19, which was fine tuned with image augmentation, got 96% of accuracy. So this is how our transfer learning and pre-trained models making effect in our image processing or image classification. So I had deployed this my model on render. so we can have a live demo of this application. For example, if we if I have to use this web application, I have to simply upload an cell image. Like if we have to see this cell image contain of malaria infection, so just we have to click this button analyze, and it will like show us that this cell image is parasiticide or it contain the malaria infection. So let's try it with non-infected cell image. So let's upload this and it will result in uninfected. So this is how our pre-trained model and transfer learning is making impact on the accuracy of our model, uh, and this is this is the impact they are making on current state of art in image processing. These are the references I had used, like research paper on ImageNet classification with deep convolutional neural network, or we can say different research papers. And thank you these researchers for these beautiful solution for image processing tasks. So you can also, if you want these collab notebook or this presentation, you can simply write down me at my mail address, as it is already shared with you all. So thank you all for joining me in this webinar session. Hope you will attend like all of others. So thank you all.